Let's suppose that they have this hydrograph here, and let me call it QT and T. And let's suppose that you have this hydrograph, which typically for the Po River is like that. And so if you have here January, and this is the subsequent January, and this is the subsequent January, basically the idea was for each year, this is 1 year, to get the top value, and for the second year, the top value. One value per each year. This is very simple to extract. Even if you work with a pen, with a pencil, they used to work with hydrographs, with graphs over the graph. It's very easy to read the highest value per each year. And first of all, you know, it's not a coincidence that I draw this picture in this way. For the Po River, we have two basically high flows periods. One is in May, June, and the other one is in October, November. And there are two low flows periods. One is in summer and the other one is during the winter. And this is typical, this river flow regime with two peaks and two minimums every year is typical of the continental climate, what is called continental climate. The continental climate is basically the climate that you find in the continental part of Europe, in the continental part of the United States. It's the climate that you find at middle latitudes, basically 45 degrees of latitude, in the middle of the continents, where you don't get the influence from the sea. Okay, if you move in Italy, for instance, toward the south, close to the sea, the river flow regime has one peak and one low flow period. But in the continental climate, you get something like that. And for the Po River, usually the most important high flow period is October, November. It's the first high flow period is much long lasting, is lasting longer, but typically the highest peaks are observed in October, November. Sometimes we got floods in the Po River in May, June, but they are very rare. I am making these considerations to stress a concept. The first thing when you handle data that you have to make is to, like when dealing with the river flow data, the first thing that you have to make is to draw the hydrograph and look at it and understand what kind of river you are dealing with. Understand if the data look fine, because you may see, for instance, at a certain point an observation here, or a zero, and clearly this is something that is may be due to errors, so you may decide to reject these observations. So you see if the data are reliable, and you see the physical process behind it. Okay, this is extremely important. Look at the hydrograph and try to understand what's going on. Okay, and then these people extracted, we are still extracting according to the annual maximum method for each year they peak. And what do you get then? Suppose that you have capital N years of observations, and suppose that you get the annual maxima, then you get capital N annual maxima. Okay, and now what is the purpose? The purpose is to describe the probability of occurrence of this random variable. The random variable is the annual maxima, for which we have collected capital N outcomes. Okay, so the purpose is to describe the probability of occurrence of the random variable annual maxima, or annual maximum. Maximum is singular, maxima is plural, if I'm not wrong. For this random variable, by doing this selection, we collected capital N outcomes. Okay, now the next step is to find a probability distribution, an analytical function describing this frequency of occurrence, which is equivalent to probability, which we may consider equivalent to probability. One first consideration, you understand that this process of describing the probability for this random variable is reliable if capital N is huge enough. Suppose that you have only 2 years of observations, you easily understand that this method could be unreliable. The statistical probabilistic methods are reliable if they are supported by a huge amount of information, namely if they are supported by data, extended enough data. Okay, this is a first consideration. And then let me introduce an assumption. 2 assumptions, sorry. First one is that these outcomes, these data, are independent. What does it mean independent? It means that the occurrence of one annual maxima has no effect, no impact on the occurrence of the subsequent one, of the next one. Why do we need this assumption? Because let's suppose, which is counterintuitive, let's suppose that they are related. So basically, let's suppose that I have an event like that. There is only one possibility to make 2 annual maxima related. Let's suppose that you have an hydrograph which is done in this way, with January placed here. And let's suppose that you have a flood occurring here. So basically, if you take the annual maxima for the previous year, you take this value, and for the subsequent year, you would take this value. And implicitly, you would treat them as 2 different floods, 2 different numbers, 2 different floods. But you see here that this is a unique event. We are interested in describing the frequency of occurrence of these events. This is one event, it's one occurrence. If I use the annual maxima method for a flood that falls across December 31st, I would take 2 observations for the same event, which is not, I would treat them as 2 events, while they are not. I need to assume independence. Is it clear? The reason why I need to assume independence. This is one event. I want to describe the frequency of occurrence of floods, and therefore this occurred just once. But if I make this selection of data, each data for me implicitly represents a flood. If I make this selection, I would end up with estimating 2 floods for this unique event, which is not physically correct. This is one. So I need to assume independence. Of course, you may say it's very unlikely. For the Po River, it's almost impossible that you get a flood that crosses between December and January. So if I take the annual maxima method, the events are much likely to be independent. And this was one motivation leading these people to select this, to devise this method. They wanted to make sure that the events were independent. By taking one event per each year, of course, it's very likely that they are independent. In the Po River, floods occur in October, and in December, the river flow is already slowed down, so the annual maxima is fine. You have only just to be careful for those rivers where floods may occur in December, January. But it's easy to check. If you look at the hydrograph, it's easy to check. You immediately see that the flood is 1. And this is extremely important. Another reason why it's extremely important to look at the hydrograph, because you can easily see if you have a flood crossing between December and January. Okay, so there is an assumption, yeah, please.
Is it mandatory to consider the time interval between January and January?
You mean it is appropriate to consider the time interval between 2 observations?
Yes.
Yeah, this is another possibility. I will mention to you this possibility later, because there is some criticism for the annual maxima method, and therefore people proposed different methods for selecting floods. And I will mention to you later this, and I will make consideration of the time interval, okay? Perfect. Okay, so first assumption, independence. Let me write it somewhere. I also need to, in my notes, I realize now that this is not, the assumptions are not listed. And I need to make a note here, because, independence is, let me see if I have, independence is, there is a Wikipedia page, so it's extremely easy to link it. Okay, let me see it later, because it's a bit slow. The second assumption, which is extremely important, is an assumption that basically leads you to consider that the frequency of occurrence of floods doesn't change along time. And this is important because I told you that we are using data to estimate the probability distribution. But I also said that this data set needs to be extended. Okay? So if the data set is extended for, let's say, 100 years, this is perfect for us. Like the Po River, 90 years, perfect. And at the end of the story, I end up with a probability distribution describing the frequency of occurrence of floods for the Po River along this 90 years long window. I need to assume that the frequency of occurrence didn't change along this period, because otherwise, what I estimate is not valid for the whole period. And this is something that may be not satisfied, because climate change, land use change, human impact, and I'm particularly interested in this course in human impact. So I will talk to you later about the human impact and how the human impact can influence this estimation process. So I need to introduce this assumption that basically means that the frequency of occurrence didn't change a long time. This assumption is called stationarity. I need to make a specific treatment on the notes. They are not treating it now, because this second assumption is extremely debated today. There are many textbooks, many scientists saying that climate change, land use change, human impact make the assumption of stationarity unreliable. There is a, let me see, if you Google for, let me see if it is fast enough. If you Google for stationarity is dead, what you see is this first paper in Science, published in 2008, which it's also easy to read. I may link it. I'm sorry, you know, the network is a bit slow. Which talks about, you know, water management, and says basically that climate change makes the assumption of stationarity unreliable. Okay, this is one contribution. And this paper was highly criticized by other researchers. And let me see. There is, for instance, here on critics of stationarity is dead. And basically, if you click here, you get a very recent paper, 2015, which basically wants to reply to a lot of criticism that was moved against the previous contribution. And it's interesting to see this reply. And basically, one of these contributions of criticism was written by me with a Greek colleague, and we called the contribution "Stationarity is Immortal," because I don't want to spend time on it now, but what I want to convey is that this assumption is debated. You have to know that. But let also me say that from a technical point of view, it's still assumed. And basically, my criticism to the death of stationarity says that unless you have an alternative assumption to introduce, we need to stick on stationarity, because we need to make design. We are engineers, and in fact, the other authors of the other paper were basically not engineers, they were geographers. From my point of view, I am an engineer, I need to design. So unless you give me an alternative hypothesis, stationarity is, you know, is a working assumption that is still very useful. This is what I mean to say. Okay, perfect. These two assumptions are, anyway, to keep in mind. Okay, at this stage we have n data, capital N data. So what is the probability distribution? Let me quickly get to the target. There is a probability distribution which is widely applied in the annual maxima method. And it's widely applied because it is extremely flexible and proved to be very useful. And this is called, so this is the second probability distribution that I introduced to you, because I introduced the Gaussian first, and the second distribution, which I am introducing, is the Gamble distribution. There is a debate in the literature about the pronunciation here, because Gamble was a German, so the pronunciation probably is Gumbel. And in Italy we say the Gumbel distribution, we say distribuzione di Gumbel. But in the American and English literature they say Gamble. So some colleagues from Germany told me that the pronunciation is Gumbel, but still, you know, sometimes I change. Okay, so the Gamble distribution, it is described here. And it is also on Wikipedia, and let me see if on Wikipedia is, maybe there was the link on the other, sorry. There is the link here. Let me see if, yeah. Here is the Gamble distribution. And basically, you see here, this is a graph of the probability density for different parameter values. I will explain to you what the parameters are. And this is the integral. Basically, this graph is the integral of this one, because it is usually given the gamma distribution, it is usually given in the form of the probability, cumulative probability, not probability density. So basically, let me see, because I am used to write it in different ways. So this is the formula, and okay, it's just 1 second, I need to, okay. So, let me write it on the blackboard. I'm sorry, gamma, it's better if I keep it. So, capital P of x, of lowercase x, is equal to e to the power of minus e to the power of minus x minus me divided by beta. And parameters are me and beta. Let me see if the symbols are the same. Yes, me and beta. Okay. This is the analytical relationship. And two parameters. First of all, please learn, we need to learn this probability distribution by memory, because otherwise we cannot carry out any of the exercise that we will introduce. It's very easy to use. It's an extremely useful distribution, very simple to use. We will see an example here. It's extremely simple, but on the other hand, you know, to learn by memory, it's a bit, because there are two exponential, but it's not so difficult. So please make an effort. And you see here, it is written in the same way. It emphasizes here the dependence on the two parameters. Look at the notation. I didn't use the same notation because I used the capital B. Sorry for that. Here they use the capital F. And also here they put emphasis on the dependence on the parameters. But basically, you know, please focus on the concept. It's the focus, the concept and the results are the same. And now, how can we use it? Sorry, two parameters. So more or less the same flexibility of the Gaussian distribution. And here you can see on the top a graphical representation of how it looks. And you see that the density is skewed, is tailed, the long tailed. You see that it's not symmetric, okay? And you may also see that it's not highly asymmetric, but still it's a bit asymmetric, which is fine. I mean, for the floods it's fine. And here you can see the integral. Okay, now, what is the next step to use this distribution? The next step, we have two steps now. To estimate the parameters, me and beta, this is the first one. And once that we estimated the parameters, and therefore once we defined the full shape of the probability distribution, we need to invert it to compute x depending on probability. Because this is our problem. We have to estimate the peak flow depending on its frequency of occurrence, depending on its return period. So let's focus on the first step, how to estimate the parameters. And again, in this case, I need to introduce two relationships that you need to learn by memory. And don't forget that we have the data. So to estimate the parameters means fit the distribution to the data, fit the distribution to the purpose, and the purpose for us is represented by the data. We need to describe the frequency of occurrence of the data. And therefore, at this stage, we have to use the data. Yeah, please.
What about the one? In,
Say again.
what about the one? No, if you scroll that up. Yeah, here.
Yeah.
If X is 1, no, the formula.
Yeah, correct. One.
1 minus. Here we should, don't you think we should have 1?
Just 1 second. Why? Because this is the cumulative distribution. It's a matter let me see. It's a matter of probability of not exceedance and exceedance. Let me see. Let me just, yeah, correct. This is a correct observation, but let me see. It's not 1 minus. The cumulative distribution, okay. So basically, I think in this case, this is, just 1 second. One minus is because in this case it's I think I don't understand really why Wikipedia does that, but I think the difference is just with respect to my writing, they use the complement to 1. So basically, they wanted to get, let me see, because in this case, if you get this, so basically this is the probability of exceedance, while in their case it's the probability of not exceedance. Okay, let me just postpone this discussion. I think it's a matter of probability of exceedance rather than probability of not exceedance, but I don't want to make a confusion at this stage. Let me postpone this discussion after the break, okay? So basically the difference is just the complement to 1, and basically it's, I think it's a problem of symbology, but I need to make it clear. Okay, let me postpone this. So basically, let me go back to the problem of estimating the parameters, and then we will clarify if I am estimating the probability of exceedance rather than the probability of not exceedance, because they are the complement to 1. Basically, if you get the probability of not exceedance of a flood that is 0.95, it means that the probability of exceedance is 0.05. And because they are the complement to 1, you understand probability is varying from 0 to 1. So basically, if for a probability of not exceedance, you compute the complement to 1, you get the probability of exceedance. So let's keep this doubt a bit, let's pause about that, and we will define later after the break if this is the probability of exceedance or the probability of not exceedance, okay? But the problem of estimating the parameter doesn't change. Perfect. So basically, let me now focus on mean and beta. And you have suggestions here for estimating them. And I am using two relationships here, which are these ones. Basically, beta is equal to, let me write down and then I explain to you the meaning. So beta can be computed as the ratio between sigma, and I am explaining to you what is sigma in 1 minute, and this constant, which is 1.283. I'm not providing the theoretical proof of this relationship, okay, because I don't want to discuss this, I need to define what is sigma. Sigma is the standard deviation of the data. What is the standard deviation? The standard deviation is basically an estimate of the variability of the data. The higher the variability, the higher the standard deviation. And it's estimated in this way, with this relationship. Suppose that you have capital N observations. You estimate the standard deviation in this way. Basically, it's equal to 1 divided n minus 1 times the summation for I equal 1 to n of Q max I minus m squared, and everything is under square root. So basically you get the difference for each of the data and the average of the data. M is the average. Arithmetic mean. So you get the annual maxima, you compute M, which is the arithmetic mean, and you compute the difference between each data and the arithmetic mean. Difference squared, you compute the summation over all the data, divide by n minus 1 and square root. Okay. This is beta. Now I get to I need to compute mean. So one concept which is important, basically what I did here is to estimate one parameter of the distribution, to estimate beta, depending on two statistics of the data. And the two statistics are the standard deviation, which in turn depends on the mean of the data. So what I need to make is to compute the mean of the data. The data, I remind you, are the annual maximum floods. I need to compute the mean of the data. Once that the mean or average is computed, I compute the standard deviation. These statistics can be easily computed with Excel. And then I get to beta. Okay, now I have to compute mean. Mean is equal to m minus 0.45 sigma. So basically what I'm interested in are these two relationships. Okay. So the distribution is estimated. There is one question still. You may wonder, okay, I got this data, and I estimated the parameters of the distribution. And your question could be, but how can I make sure that the distribution is working well? Okay, this is a question that we will reply to in the next hour. Now, let me assume for now that the distribution is well working, and let's move another step forward to the estimation of the peak flow. Given that we have this distribution, and let me suppose for now, to anticipate the answer that I need to give to you, let's suppose for now that this is the probability of not exceedance, okay? Because this is what I'm convinced of, but I need to make sure by looking at the Wikipedia page during the break. But let's suppose for now that this is the probability of not exceedance, okay? This is what I'm quite sure to remember, but I didn't notice that the Wikipedia page was displaying the complement to 1. So let me assume for now that this is the probability of not exceedance, for which we have estimated the parameters. Okay, so basically to move the step forward at this stage, I need to specify the probability for which I want to compute x. So I need to specify for what probability I want to compute the design flow. Okay, so let me introduce